So don't forget, in case you have already started in on it, that, I drew too many electrons on there, that this has a 2- charge, meaning that 2 electrons somehow were added to the whole system. It's best to draw those electrons on the more electronegative atom. So I'm going to add those to 2 of the 3 oxygens. It's not the prettiest structure, but it's correct like that. Okay, so if you want to check your structures, I'm going to go ahead and write formal charges up there as well. Okay, so just to kind of like remind us as we're going through these, because we're going to do Lewis structures the entire rest of today, and we have to feel really comfortable with them because in 11 on Monday, we're going to move on to looking at shape, which I hear you guys have been doing in lab already. So we need good Lewis structures to be able to do that. If you don't have the right Lewis structure, you can't predict their shape. Okay, so first thing that we always do is draw the atoms with the correct electrons, then start forming bonds. And when you do that, you need to make sure that for carbon, nitrogen, oxygen, and fluorine, you're satisfying the octet. There's an extra C in there. Okay, and then for today, we're going to talk about the exceptions to the octet. So there are a couple that will underfill, meaning they won't have a complete octet, and then there's some that will overfill, like they could have an octet or they could have more than that. Okay, and as part of this, you want to consider, do they have the bonds that we would predict? Like, do we see carbon having 4 bonds? Do we see oxygen having 2 lone pairs and 2 bonds? That's not like a requirement, but a lot of the time it can be a really good guide. And sort of related to that is the formal charge. So we'll use this one we have up here as an example. Let's just start by reviewing how do we do formal charge and like how do we know if it's telling us the molecule is good or bad, okay? So just looking at this structure here. So we drew out the atoms, we added 2 electrons, so I added them to the more electronegative atoms. And then I started pairing things up. So like these 2 only needed a single bond because they already had 7. So They just needed, they kind of were behaving like a halogen. They just needed a single bond to complete their octet. But then this one needed 2 bonds, and thankfully there were 2 carbon electrons that it was able to share with, okay? So that's how we got this structure, one of them being a double bond and 2 of them being singles. And then doing the formal charge is really very closely related to what do we predict the bonds to look like. So carbon, we predict it to have 4 bonds, that's like what we expect it to have, and no lone pairs. Well, when we do that, when we use the predicted number of bonds, we end up with a formal charge of 0, which is basically just an indicator that it's behaving the way we would expect it to. Okay, same thing on the oxygen. We expect oxygen to have 2 bonds and 2 lone pairs, and it does, so it has a formal charge of 0. Is there a question? Yeah.
Might I ask, like, what the orange dot is? That like when you have...
That's those extra electrons. So I did them in a different color to remind us that because it had a 2- charge, it must have gained electrons, probably from a metal, you know, some stray sodium or whatever. It gained those 2 electrons, so I just wanted to show you, like, that's where I decided to put those 2 electrons. It could have been on any of the oxygens, but oxygen, not carbon, because oxygen's more electronegative. So if I toss an electron into the system, they're naturally going to go towards the oxygens. So let's count up basically the subtraction for formal charge to verify that those 2 we've already talked about are 0. So the way we do that is we want to just look at the electrons that are immediately surrounding the atom. So not counting the whole bond, just the ones that are like right next to the atom. And we're going to take the number of valence electrons that it started with, so 4 in the case of carbon, and we're going to subtract the electrons that it has now in this molecule. And by has, I mean immediately surrounding it. So it started with 4, it ended with 4, that's why it's a 0 formal charge. Same thing with the other oxygen. It started with 6 because it's in the 6th column. It ends with 6 because it's got 6 immediately surrounding it. And so it has a formal charge of 0. Okay, the other 2 oxygens, they both started with 6, but now they've got 7 surrounding them. Okay, so that's why they're -1, 6 minus 7. Now, that should kind of make sense, because by saying a formal charge is -1, you're saying it got an electron from somewhere. Usually when we do formal charge, it's that it gets an electron from one of the other atoms in the molecule. In this case, it literally just got it because it was a -2, and we said we have to plunk those electrons down somewhere. So we plunked them down on those oxygens, and that's why it has that charge. So every time your formal charges are going to add up to the overall charge. So like it had to be equal to -2 because there was a -2 charge. So this all should kind of make sense in this case. I want to do one more example that makes less sense in a second, just to show you that like this can happen even when we don't have a polyatomic ion, even when there wasn't charge on that original species.
So you have to add 2 electrons to 2 of the oxygen.
So you don't want to make the mistake of trying to add them to the same oxygen, because then you would basically complete the octet for the oxygen without it being bonded to something else. Also, just remember, like, electrons want to spread out as much as possible, so spread them out as much as you can. But spread them out to the things that want them, right? Like, the oxygen's going to have that good pull on the electrons, so it's going to grab them. Okay, so now what am I doing here? Those are the resonance structures. Remember, if you have equivalent structures, where all that's changing is where that double bond is, or triple, whatever, that additional bond. You need to draw all three, in this case, versions. There's one later on that we did in my other class that had 6 resonance structures. That was a mess, but there you go. So we've got 3 different versions, and they're all equivalent. They're just different oxygens are taking that extra bond. So what we say about this is that it's an average of all 3 of those structures. And we would say that the bond order is 1 1/3. For each one of those CO bonds. And I have notes about this at the end of today's notes. And I'm probably not going to go into them in detail because we've actually been talking about it every time we talk about resonance structures, like last class and today. And we'll keep talking about it. When you have a single bond versus a double, the single is always going to be longer and weaker. And as you add more shared electrons in there, so a double bond, the bond pulls in tighter because it's got more and more attraction there. And all that additional attraction makes it harder to break it, or it's stronger. So when we look at this, it does not have a strength or length that corresponds to a single or a double. It basically looks like 1 1/3. So it's a little bit stronger than a single, it's a little bit shorter than a single, but certainly not quite, to a double. Okay, and that's how we know this is a real thing. Because when we look at these bonds, that's how they really look. Those atoms are physically further apart from each other because that bond is longer than what a double bond would predict. Okay, so kind of keeping these 4 points in mind, did I see an example of this? Okay, the way that I'm approaching, I think last year, I took this I'm going to try both methods of teaching Lewis structures, and now I'm fully on board with the way I'm doing it this year. And I'm finding more and more that formal charge is used as an explanation for why we pick a particular structure, but not we don't have to use it that frequently to get to the right Lewis structure. So I think you guys are getting an intuition about what Lewis structures should look like, and not even having to rely on the formal charge, but it's still something we should be aware of because it is the official way that we designate which of 2 equivalent structures might be correct. So if you remember, we did this one at the end of class where we said that top structure is the one we would predict. Well, from all the examples we've done, I think, so number 1 versus number 2, in all the examples we've done, I think you guys are getting an intuition that one makes the most sense. When have we ever seen a carbon with a lone pair? We haven't, right? We have all the examples we've looked at have carbon having 4 bonds and no lone pairs, and the nitrogen has always seemed to have 3 bonds and 1 lone pair. It's not to say that it couldn't go away from that, but that's our expected thing. This is what I mean about, do the atoms have the number of bonds that we would predict based on the periodic table, okay? So we can, however, use the formal charge as a defense, a more official defense of why that one makes sense. Because if we look at the formal charge on this one, all of them are 0. Okay, the carbon, nitrogen, the hydrogens even, those are all 0. In number 2, we end up with a -1 on the carbon and a +1 on this nitrogen. And when we use formal charge as a defense for why we think a particular structure is better, it's always better the closer to 0 as possible. So in this instance, that's the only defense we need, is that structure number 1, all of the atoms have a 0 formal charge. That is much better than structure number 2, where they don't have a 0 formal charge. I'm talking about each individual atom, not the sum. The sum of them has to be 0 because this is not a charged species, not a charged molecule. but each individual one is closer to 0 in that first structure. They're equal to 0, okay? If you have to have non-zero, so there will be times like the carbonate, right? Like this one we just did, where we have to have non-zero formal charge because the molecule has charge. It has a 2- charge, so we're gonna have to have some amount of formal charge on there. So if you have that, the preference is to have negative charge on the more electronegative atom. So if there's non-zero formal charge, put it on the more electronegative, put negative formal charge on the more electronegative atom. Or another way of saying that would be positive on the less electronegative atom. And you can always look those numbers up on the exam equation sheet. There is definitely a trend based on starting with fluorine and moving away from it. But like if you just need, actual numbers, you can always look on there. Okay, so like I said, keep in mind these 4 steps. Make sure that you're putting atoms with their valence electrons before you do anything else. Then start bonding them up, making sure to satisfy the octet for carbon, nitrogen, oxygen, and fluorine, and not go over it for those. Try to use the correct predicted number of bonds if that's possible, and then use the formal charge if you need to decide between 2 structures which one's better. You're probably not going to have to. You're probably going to be able to just use, do they have the correct number of bonds that I would expect? Okay, so knowing that, we are now going to go to over and under filling. So let me summarize kind of the guidelines here, and then we'll look at the examples. Okay, by underfill, I mean the atoms we're about to talk about will not have 8 electrons surrounding them, okay? They do not end up having their octet satisfied, but they still are able to form stable molecules. So this is going to be molecules that have beryllium, which I'll show you the periodic table in a second. And then in column 3, boron, aluminum, and I saw that you guys had this in lab. I wasn't going to mention it, but gallium is right under aluminum. It follows the same trend. But these are in column 2 and 3 of the periodic table. So it's a very I have it highlighted on the periodic table that I'm going to show you, but it's a very obvious location. So go to your periodic table when you're wondering oh, is this something that has to underfill or does it have to follow the octet? I'm going to show you kind of visually how to remember those because I don't expect you to memorize a list. That's not what we're doing. Okay, then we have the ones that have to follow the octet, right? Carbon, nitrogen, oxygen, and fluorine. And then we're going to have ones that overfill, meaning they have more than 8 valence electrons surrounding them. And this is going to be, it's written right up here. Atoms at n equals 3 or higher. So by n equals 3, we mean the third row, which would start not with these guys over here, but would start with silicon, phosphorus, sulfur, chlorine, etc. And then going down to the next row, you end up getting, is that selenium? Or selenium's over here, I think. I think this is germanium. Oh, see, now I'm going to have to look. It is germanium, arsenic, selenium, and bromine, okay? But that continues on. So let me show it to you on the periodic table. So n equals 3. Now, when I write it on the periodic table now, because I'm assuming you guys remember this from last semester, yes, it's the third row, but that corresponds to the third energy level of where those electrons are. So like third step out from the nucleus. Okay, so green are the ones that will, not sure why I have that circled. Greens are the ones that are going to underfill. Blues are the ones that follow the octet exactly. And then yellows will follow the octet, like will have at least 8, but could fill more. So they might have 10 or 12 electrons surrounding them. So we're going to do examples of these. The underfill ones, I'm going to leave those until we actually do the examples to explain why it happens. Just know that it's going to happen for those, and the number of bonds that it'll form corresponds to its column, just like the other elements do as well, but not in the like exact way. So if you look at beryllium, it's in column 2, it's going to form 2 bonds. Okay? Boron, it's in column 3, it's going to form 3 bonds. And when I say that, I mean and no lone pairs. Like, yes, nitrogen's going to form 3 bonds too, but it's also going to have a lone pair. We have this weird thing where we see, boron and aluminum forming 3 bonds, and then it's got no lone pair. So it only actually has 6 electrons surrounding it. So we'll do examples of those ones in a second. Go ahead.
The yellow ones overfill.
Yeah, so the yellow ones are the ones that overfill. And let's talk about right now why that happens, or why it's able to happen. So I'm going to redraw this orbital diagram. I guess I have a little more space down here. I'll do it down here. Okay, so if we look at carbon, because it's one that's, strictly following the octet, it's got the 1s is filled, the 2s is filled, and it's got a couple in the 2p. Okay? So it has the capacity to have 4 more electrons surrounding it in that n equals 2 energy level for a total of 8, right? Filling up the s and the p, so it would have these 4, and then 1, 2, 3, 4, another 4 that could surround it. But if we wanted more electrons in there, we would have to jump up to an entirely other principal energy level. So we're down here. It can only hold 8 down here. If we wanted to try to force more electrons on carbon, it would have to go out to n equals 3. Okay? That just because there's no more spots. If we look at silicon, though, so similar to carbon, but just one step down, we've got the 1s, 2s, 2p, 3s, 3p, and then don't forget the s's are at 1, at 2 we have s and p, and at 3 we have s, p, and d. So we actually have these d orbitals up here, and then if we get to 4, we get the f's. So in silicon, it's got these filled. And it looks pretty similar to carbon in that it has 2 in the S and 2 in the P. And we still have those additional 4 spots, right? 1, 2, 3, 4, where we could put electrons. But look at all these guys. We have all these additional orbitals that do not have any electrons in them yet. Okay, so that is why once you get to the 3rd energy level and any after that, you can go ahead and add more than 8 electrons because 1, 2, 3. Now we're at n equals 3. There's actually an electron capacity of 18 in that principal energy level. So in theory, we don't actually see elements that have this many, but in theory, you could have 9 pairs of electrons surrounding an individual atom because there are enough orbitals for that. Okay? So we're going to start with that. We're going to draw molecules that overfill. Just make sure you realize that this can only happen once you've got d orbitals, and that is minimum n equals 3, and then any beyond that. Okay, any clarifications on this before I step away from the periodic table? All right. Okay, so let's go ahead. I want you guys to let's do the two of these together. Sometimes I like having tons of extra room, and sometimes I just don't need it. So let's do SF4 and SF6. So go ahead and follow those same approaches. Draw the atoms, draw the correct number, start bonding them up, and let's see where it takes us. Oh, I'm going to send around the roll. So I do finally have a roll. If you're not on this list and you're here, then come talk to me, because either I made a mistake or you're not actually registered for class. So just check off your name under January 30th and pass it back. I don't know. Oops. Okay, so I'm going to start bonding these. So I think the weirdest thing that comes out of this first one, SF4, is that all of a sudden we've run out of lone electrons, not lone pairs, but electrons that don't have a pair. Like in the past, we've only taken individual electrons and created a bond, but now we've got pairs and we know we need more bonds, and we're having to snag from a pair. So you could take both of the electrons from a pair, or you could take one from each. It doesn't really matter because in the end, you're going to write them as a pair. So what this molecule is going to look like is sulfur with 4 bonds with the fluorines that each have 3 lone pairs surrounding them. Like this. Okay, so those are a nice, like, cleaned up structure. So however you take the electrons from sulfur, just be aware you're going to have an even number left over, and you need to write them as pairs. But that's the big difference here, is that we're now forming bonds with things that we thought should be left alone, like they should stay as lone pairs. Yeah?
Is there ever a time where there's just one singular,
No. Yeah. If you end up with one singular electron, you did something wrong. Yeah. So you may start doing that in organic chemistry. Usually those are going to be super reactive species, though, and they're going to just react and form something else anyway. They're called radicals. Okay, so then on the other one, this one actually works out kind of nice. You have 6 things that need to be bonded. You have these 6 electrons around sulfur, so it's just every single one of those electrons forms a bond with a fluorine. And maybe it freaks you out a little bit because you're like, there's 6 things surrounding that sulfur, which means there's 12 valence electrons. That's okay because it has those d orbitals. Same thing over here. It's got 10 valence electrons. 2, 4, 6, 8, 10. That's fine. Okay, it's using those d orbitals to hold those extra electrons. Now, if that was oxygen, it would not work. Like if I had OF4, that molecule does not exist because there is just not enough electron capacity around oxygen to have that many electrons surrounding it. It just doesn't have the orbitals for it. Same thing with OF6. That would not exist. So sometimes you'll see homework questions that are like, you know, SF4 is a stable molecule, but OF4 is not. You know, select the answer that it best explains why. Okay, and then just one note about formal charge, because this is kind of an interesting thing. We said before that if things have the bonds that we expect them to, which for sulfur would be 2 lone pairs and 2 bonds, that they'll have a formal charge of 0, right? Which is a very good, stable state. Well, if we look at the formal charge here, so I'm just going to do it on this sulfur first. Remember, we only count the electrons that are immediately surrounding the atom, not the entire bond, just the ones that are immediately surrounding it. So sulfur started with 6, and now it has 1, 2, 3, 4, 5, 6. So this is apparently a stable form of bonding that sulfur can have that still gives it that 0 formal charge. You certainly don't need to remember that. Like, you don't have to remember, oh yeah, sulfur can have 4 bonds and a lone pair. Because look, it can also have 6 bonds and no lone pairs. That also has a formal charge of 0. Started with 6, has 6 now, so the formal charge is 0. So we can actually get really stable molecules that have 0 formal charge on them that aren't necessarily the bonding we would predict. Okay, especially once we get to these higher order ones. When you're talking about carbon, nitrogen, oxygen, and fluorine, they very much follow the expectation. Okay, so that's our first example of overfilling. Now we're going to go on to 2 examples of underfilling that are the column 2, beryllium, and then column 3, boron, aluminum, and gallium. So I'll pair these guys up too. So BeF2 and BH3. So go ahead and draw both structures for these ones. Same approach as we've always done. But knowing that beryllium's going to form 2 bonds and no lone pairs, and boron's going to form 3 bonds and no lone pairs. And you'll see why pretty quickly. Okay, so I'm going to start with BH3. Am I going too fast? Good? Okay. I'm going to start with BH3 because this one is just like so obviously there's nothing else we can do. So boron has 3 electrons surrounding it. I'm telling you that it bonds with 3 hydrogens, so those each have 1. So like there's literally nothing else we can do here. If I tell you that this is a stable molecule, then it is, and this is how you would have to draw it, okay? You'll also get boron, aluminum, gallium. You'll see them bonding with like halogens a lot of the time, like aluminum trichloride. That'll have the single bond to the chlorines, and you just won't have any lone pair on the boron. So it's very common that these column 3 elements still form covalent compounds, still form 3 bonds with those 3 valence electrons. They just don't have any lone pairs. And it's just something you need to be aware of, okay? In this case, there's no way you could have like mistaken it. You might be like, oh, did she give us the wrong thing? No, this is just how it looks. Now with the beryllium difluoride, that one is similar. It'll just have these single bonds, no lone pairs on the beryllium. Fluorine's octet is satisfied, so that's good. But the beryllium's is not. It just has those 2. Now, we could do it a different way so that the octets would be satisfied. We're not going to do this. This is not correct, but I'm going to show you what it could be and why it's incorrect, okay? So if I took, I'll draw it the first same way to start and then show you what happens. Okay, if I took a pair of electrons from the fluorine and shared it between the fluorine and the beryllium, so both electrons are coming from the fluorine. Okay, so I'm going to erase that now and put it as a double bond. That actually would satisfy the octet for both the fluorine and the beryllium. So people will commonly think, oh, well, that must be the case because why wouldn't we satisfy the octet? I am getting so much spam lately. It's so annoying. that would satisfy the octet, but I'm telling you that's not what happens. When we look at this structure, we see 3 lone pairs surrounding the fluorine, okay? And we do not see a double bond kind of length between fluorine and beryllium, okay? So the first one is the correct structure. The way we can defend just while we're drawing it is by looking at the formal charge. Okay, so take a couple minutes. I want you to do the formal charge for both the top one and the bottom one and see how they compare. Okay, so first one has 0 formal charge for everything. So pretty good structure then is what we're saying. The second one, -2 on the beryllium and +1 on the fluorine. Okay, so they're not close to 0, but also we said that if they're going to be non-zero, you better put the negative charge on the more electronegative atom. This is the exact opposite of that. I think beryllium's electronegativity is like 1.5 and fluorine's is 4. So this is the exact opposite we would expect, okay? So it's another good example of formal charge indicating to us which one is the better structure. All right, so we've done underfilling, overfilling, and 46. Okay, I think we did one more in my other class. Let me think which I want to do. Okay, this is the notes that I told you about that I'm going to put a big question mark here. Like, it's not particularly useful information. We're going to talk about it in chapter 7. But this is the main thing that I'm like formalizing now, is showing you guys that strength and length correspond to the bond order. So this one is length. So longer when you have a single bond, it's shorter and shorter with more higher bond order. And then strength, you can see it gets the kilojoules. It means like how much energy, that's why the previous 2 slides are talking about, how much energy to break apart those atoms, okay? So single bonds are weaker, and as you get more bonds, it's stronger. And remember, the term we use for this is bond order. So 1, 2, and 3, or if it's something that has resonance or resonance structures, then it might be not a whole number. So for the last one, I just want to go ahead and let's do this one, PO4 3-, and we'll do it together for the sake of time. Okay, so it's a 3-, meaning we've got 3 additional electrons. The oxygen is more electronegative, so I'm going to add it to the oxygens. So I'll do those in purple. So 1, 2, 3 of the oxygens are getting an extra electron. So those 3 will form single bonds with the phosphorus. And then the other oxygen that's going to need the double bonds gets to form double bonds with phosphorus. So again, an overfilling. It's now got 10 electrons surrounding the phosphorus, but that's fine because of where it's at on the periodic table. And then also recognize that these are going to have 3 more resonance structures. So to properly describe this, you would have to redraw this, but move the double bond here and have the one with 3 lone pairs up there, or move the double bond here or there. So technically then the bond order here would be 1 1/4. 4 regions, but 5 bonds. So 5 divided by 4 or 1 1/4. You're saying I have to spread out that additional bond over those 4 regions. That's where that extra quarter comes from.
Can you explain the bond order again and how you?
Yeah. So let's pretend that this extra one wasn't there. They would all be single bonds, right? So we have this additional bond, but in reality, I'm going to do the dotted thing. In reality, that additional bond is actually spread out over all 4 of these. So it's like we took one bond and put a quarter of it in each of those places. Yeah, so that's where we get the 1 1/4 bond order. And they all would look similar, all similar length, all similar strength. So on Monday, just keep an eye on your email. It's so tired of the whole 2-hour delay thing. But my kids they were out forever and then they keep getting this 2-hour delay, and I haven't done my turn yet in staying home and making sure they get on the bus. It's been Dad's job the last couple days. So I may need to do remote on Monday if they have yet another 2-hour delay. It looks like it is going to be cold again, but like, geez, you know how much less annoying that is to drive your kid to school or to the bus stop than to have to go to work 2 hours later? I don't know why they think that's a better idea. It's not like they're going to be that cold in my nice toasty car. Whatever. Anyway, just keep an eye on your email. Hopefully that won't be an issue, but possibly. Also, it's going to be -11 tonight. Like not wind chill, like actual temperature, which I think is the coldest we've had this whole last week. So get your snuggly comforters. Okay, I'll see you or talk to you or something on Monday. Where did the attendance sheet end up? Did everybody get that? Yes.
I put the
All 6. Okay, so 1, 2, 3, 4, 5, 6. Perfect. And then write the ones that are single bonds that are -1 and everything else is 0. Yeah, that looks great. Okay, so what's the bond order on these?
It would be 6 of.
Yeah, which is 1 1/2. Yeah, perfect.
Thank you.
Yep.